Today's lesson focuses on a topic called isomers. The definition of an isomer is a molecule that has the same molecular formula or chemical formula. So for example, if we talked about something like pentane. Pentane has a chemical formula of C5H12. But then you take those 5 carbons and you take those 12 hydrogens and you come up with different arrangements of atoms. And the way that you would know that you have an isomer is that those different arrangements should all have different names. All right, so we're going through the process of naming all these molecules. That's how you know that you have a true isomer, is that when you put them in a different arrangement, they will have a different name. So there are a few different kinds of isomers that we should be aware of. The first kind are called positional isomers. So this is where the family remains the same, but again, the arrangement of atoms differs. And we assume that they have the same chemical formula. Okay, so if you want to take a second, you can count up right now the fact that both of these structures have 4 carbons, and then they have 2, 4, 6, 8 hydrogens. So both of those molecules have the same chemical formula. But when I go to name them, and this is the big thing, here, this molecule, because the pi bond is on carbon 1, this will be called 1-butene, and then this structure would be called 2-butene. So they have different names, okay, and they look different, okay? The pi bond is in a different spot. This means that they are isomers of each other. Here's another example of 2 isomers. So a functional isomer is where we have more than one family present. So when you look at this, or these 2 molecules right here, you'll notice they have different names. Okay, the first one is called propanal, the second one is called propanone, and that is because they are 2 different families, and they structurally look different. Okay, so they still have 3 carbons, they have 1 oxygen, they have 6 hydrogens. Okay, so again, chemical formula, we would write it like this. We usually put the oxygens at the end. Looks like that, and it's the exact same chemical formula, but notice that there is a C double bonded O at the one end for the propanal, and then it's in the middle for a propanone. You can also have geometric isomers, and these really only apply to alkenes and the pi bonds. And what we're referring to here is the different arrangement of atoms around that pi bond. So when you have a pi bond, different to a sigma bonds have lots of flexibility. We mentioned that before, and there's a lot of rotation around the sigma bond. With a pi bond, there is no rotation. And so the atoms that are bonded to a pi bond are locked in place. So when I look right here, I notice that I have hydrogens on the same side of the double bond. And when I look over here, I notice that my hydrogens are on opposite sides of the double bond. So when we name geometric isomers, and this only applies to alkenes, if the hydrogens are on the same side, we use the prefix cis, okay? And think of cis, I know it's not an S that it starts with, but it sounds like an S. Cis for same, and then we finish off the name, and this would be 2-butene. And then if they're on the opposite side, we use the prefix or the name trans, and then we would call it still by the same name, trans 2-butene. And you might be saying, oh, but they got the same name. Well, they don't, because we have this part cis and trans written down. That denotes that they are different molecules, that their arrangement of atoms is slightly different around the pi bond. So let's practice drawing some isomers for a few chemical formulas that I give you. So it says here, draw all the structural or chain isomers. Chain tells us that it's straight chain, okay, no rings. Of C6H14, and it says how many are there, and verify that they are all different using molecular models. And I also say to name them. This is so important that you name them, because that's the only way that you'll know, did you come up with the correct number of isomers. So what we do first is we just start off with a straight chain 6 carbons in a row. Okay, so let's just go and do 6 in a row. So 1, 2, 3, 4, 5, 6. Now we want to make sure that we don't have any pi bonds. So we just are mindful about those hydrogens. If I have all pi bonds, or sorry, all single bonds, then I should have 3 hydrogens on the first carbon, another 2 or 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So what I know is that I should have no pi bonds here. If I have a pi bond, I lose 2 hydrogens, okay? So if this formula was C6H12, then what I would know is I have to go back and stick a pi bond in somewhere. So let's name this. This is easy. This is just a hexane. And there is one isomer that we're going to use. There is nothing I can do with 6 carbons in a row to come up with a different structure or a different name. So what we tend to do is be kind of systematic, and we're now going to go down to a pentane. And I'm going to take 5 carbons in a row, and I have 1 carbon left over. Where can I put it to get a different name or a different structure? Do not put it on carbon 1. Okay, so I'm putting it there now just to show you, but what you just did was you extended your longest chain. You actually have a hexane there, and you did not create anything new. But if you take your carbon and you put it on carbon 2, then if we fill in all of our hydrogens, we now have a pentane molecule with a carbon branch, a methyl on carbon 2, and we would call this 2-methylpentane. So where else could you put that carbon to come up with a different named, different structural molecule? Well, you could put that methyl group next door and put it on carbon 3. So if I put it on carbon 3 here, I get, again, a new name. I'm just going to put my hydrogens in for good form, but 3-methylpentane would be the name of this. And that's another isomer. Now, where else could you put the carbon? Could you put it on carbon 4? Well, let's just draw it out here. So I'm going to do my 5 carbons in a row, and I'm going to put my carbon on carbon 4. But it's not really on carbon 4 because you know the rule. You're actually supposed to number from the side closest to the branch. So it's actually on carbon 2, and it's the exact same molecule as the 2-methylpentane. So once we've exhausted the possibilities for a 5-carbon parent, we're now going to go down to a 4-carbon parent. And now I have 2 carbons, 2 extra carbons, right, to maintain this formula. And where would I place them? Don't place them on the ends. When you place them on the ends, you just extend the longest chain. So what we could do is we could put 1 carbon each on carbons 2 and 3, and we can call this 2,3-dimethylbutane. And where else could we put those 2 carbons to get something new? Well, we could put them on the same carbon, right? You could put them right here. So you could have 2 carbons on the second carbon and call it 2,2-dimethylbutane. Could you put those 2 carbons on 3,3? No. Because 3,3, you would number that from that side, that'd be closest. It's the same as 2,2. So there's nothing else that you could do with a 4-carbon parent. And that's really it, because if you go down to a 3-carbon and you try to put in an extra 3 carbons, you could maybe put 2 carbons in right here, but that 3rd carbon, you're going to be extending it on one of those outer carbons, and these are molecules that you've already made. So in this case, you have 5 isomers that you can come up with for the molecule C6H14. I'm going to get you to try this last one on your own. So it says draw and name the cis and trans isomers. Remember what that means. Cis and trans applies to alkenes and the position of atoms around the double bond, either same side or opposite side, of dibromoethene. And then 2,3-dichloro-2-pentene. And when you see bromo or chloro, you're just going to be putting in those halogens. So you'd be putting in a bromine atom. Okay, so you'll put it in just like that, write in the Br and write in a Cl instead of a hydrogen. And I want you to also make those models and just compare them for these types of geometric isomers, and have me come and take a look when you're done.